is there anybody here who literally never ever experienced lag before while playing online? No hands. Okay, so that's the answer I expected. Let's try another one. Is there anybody here who never blamed latency for losing online match? Probably even the important one. Okay, 2 hands. So I really envy you. You managed to avoid a lot of frustration. Trust me, I've been there. As you can see, lag is a pretty common thing, and it comes into play whenever internet is involved. Today I'm going to answer some questions. What is lag? Where does it come from? What can we do as game developers to improve overall online gaming experience? I'm Mateusz Baran. I work for PixelAnt Games. I have 6 years of experience developing online multiplayer games. However, I don't find it nearly enough to consider myself an expert, and for this reason, I'm speaking to you today mainly as someone who's basically passionate about online gaming and not only creating those games, but playing them as well. The presentation is divided into 2 parts. The first one, that I like to call theory. For many of you, it might be the boring and useless one, but bear with me, it's the shorter one as well. And the second one that I like to call practice. In the first one, I'll show you the definition of the latency and deconstruct it into components so you can understand it better. In the second one, I'll show you some cool techniques that you can use to minimize impact of the latency on the actual gameplay. And that's where I'll show you some cool examples from games you might already know or even have played before. If you have questions, write them down. At the end, there will be Q&A, if we still have time, of course. Without further ado, let's get down to definition. When someone talks about lag, latency, the first thing that comes to mind is network lag, network latency. It's hands down the most common, most popular type of lag. However, this will be controversial one. I don't think that we as game developers should pay that much attention to network latency as we currently do. Hear me out. What is the most important thing for us as game developers? It's end user experience. It's what user feels when playing the game. And most often, we cannot use network latency and map it directly to the end user experience. There is better latency to do so. But let's take a look what our trusted knowledge source, Wikipedia, has to offer in this regard in terms of definitions. This definition is kind of complex, so let me use my own words. Network latency comes from the fact that we need to send the data to the server. The server processes this data and sends response back to our game client, and of course it takes some time. The better for us as game developers is input latency, and this definition is far worse than before, so once again let me use my own words. Input latency is the time it takes from user taking action to user being able to observe consequences of taking the action on the actual screen. And it consists of many steps, so let me take you through all of them so you can understand the nature of this latency much better. The first step is input device lag. Mouse, keyboard, gamepad, whatever you use. Depending on the device, the latency will be different, but it will be there. So yeah, using Office wireless gear for competitive gameplay might not be the best idea. The next step is our game client. Our game client takes input provided by the user, packs it into network packets, and sends over the network to the server. And you might be wondering, why is this latency so big, between 10 and 50 milliseconds? Packing data and sending through network is simple and quick operation. Why is that? It's because in netcode we quite often use some techniques that aim to lower bandwidth requirements of the network, so people with slower network connection can enjoy the game as well. And for this reason, we tend to send and receive data from the network in much lower frequency than our typical rendering frame rate. That's why those high values. Next is network transfer. A lot of variables here. What is your location? Because the distance between your PC and between the server does actually matter. What is your ISP? Do you use Wi-Fi? Do you use cable? For typical online gamer that has gear and internet connection somewhat adjusted for online gameplay, this will be between 5 and 60 milliseconds. Of course, the worst case scenario will be in thousands, But for the sake of this presentation, let's focus on this typical range here. Our data reaches the server. The server performs some validation. It needs to check whether it's not cheating attempts, whether maybe the context has changed and the action cannot be performed anymore. But when everything is all right, the input provided by the user is applied to the simulation running on the server, and the result of the simulation is sent back to the game client. And of course, the data travels around the world once again, but this time in the other direction. So the same rules applies here as for the previous network transfer. And finally, our game client receives response from the server. And at this stage, our client finally knows what the consequences of user taking an action actually are. And at this time, you might be even more like, what the heck? 50, 150, it's really long, and it's far longer than the previously when data went through the game client. And it's because at this stage, we need to take into the consideration other parts of our game. It's not only about networking anymore. For example, we need to render the image, so we need to use some kind of rendering engine. And quite frankly, rendering engine on its own can add quite a few milliseconds to our input latency chain. And finally, last but not least, we have output device lag. Consists of stuff like pixel response time, refresh rate, or the delay of the electronics themselves. And this whole chain of events is our input lag, input latency. It gives us whole picture that we can map almost directly to the end user experience. And the most popular one, the network lag, is only this small section in the middle. That's why I think we as game developers should put way more attention to input latency than network latency. It's because, well, when we take a look at this whole picture, we can notice things that are not obvious otherwise. For example, I mentioned the rendering engine, so let's take it as an example. We can improve latency there to have more slack on the network end. And I don't mean it like, oh, now we can have worse NetStack implementation and get away with it. No, we can provide much more responsive experience for users with higher network latency. And we can do this without even touching the network part, which is pretty cool. Let's talk about some numbers for a second. With my assumptions, overall latency falls between 84 and 426 milliseconds. In practice, we won't face neither of those extreme values too often, so let's take an average, 255 milliseconds. Still, new questions arise. Is this low? Is this high? What is our goal? What is the value we should aim for? And the answer is, as always, it depends. But there is rule of thumb, and it goes like this. As long as your game has lower input latency than reaction time of the player playing your game, you're good to go. This player won't notice anything out of ordinary. And average human reaction time is around 200 milliseconds. So it would be wise to aim for this value and probably even a little bit lower than that. Some people would argue you should aim for 180. Some would argue 160. As for me, it depends. You should know your game and you should know your audience. If you're creating chess game, you can probably create game with 2000 milliseconds of input latency and get away with it as long as you provide great feature set. But on the other side of the spectrum, we have games that revolve around quick action and response, like games that focuses mainly on competitive audience. In those cases, we need to pay way more attention to input latency, and for lower values, we should aim. Let's sum up what we have so far. We know what is the lag, we know where it comes from, and we know that we need to do something about this one, because if we won't do anything, we are in kind of dangerous place, because our average input latency is higher than average human reaction time, which means quite a lot of people would actually notice something is basically not right, would notice some shakiness, weirdness, and stuff like that. And that's where the practice part of this talk comes in, and techniques that you can use to improve perceived input latency. The first technique I'm going to tell you about today is distraction. Distraction is like we, as game developers, can pretend to be some kind of street magician. Because street magicians use hand gestures, body movement or some props to distract your attention. The real magic happens in places where you don't look. Of course, in game development industry, we want to do as many things as possible on the server side because it's safer, it gives us coherent game state. But this doesn't prevent us from adding some sugar on the client side exclusively. We can add basically as many animations, sound effects, visual effects as we like, as long as we won't mess with the game state too much. Typical use case for this technique are movement indicators in top-down games. For example, StarCraft 2, those green arrows marked in red circle, this is movement indicator in this game, and it's completely local. It's animated and being displayed right after pressing mouse button, but the unit itself moves after short delay, only after receiving response from the server. And we can see almost exactly the same indicator in other top-down games like MOBAs, League of Legends. Of course, I don't want you to take my word for it. I had to find a way to prove that's what actually is going on under the hood. And the easiest way to prove this turned out to be disconnecting the network like altogether. Let's see what we have here. We can still see those arrows. They are being animated perfectly fine because they are completely local without any delays. But Ari, in this case, game character, doesn't give a flying F about those arrows because she still waits for the server to respond. And it's not going to happen because there is no internet connection. The next use case for this technique are projectiles. Shooting rocket launcher, throwing grenades, stuff like that. Simply by looking at this footage from Quake 3 Arena, you probably won't notice anything out of ordinary. It's like quite dated game, so the graphics improved over the years just a tiny bit, but that's that. And the gameplay experience is fine as well. Let's take a look frame by frame what is really going on. This is frame before shooting any projectiles. And this is the first frame of the shooting sequence itself. We can see those distractions in place. We can see this explosion at the end of the barrel. We can see the animation of the weapon, the recoil animation. It goes back and up a little bit. But can you see anything weird about this frame? There is no projectile. We just shot a rocket, but there is none in the screen. Let's count frames, how long we need to wait for the projectile to appear. 1, 2, 3, 4, 5, 6, 7. We had to wait around 7 frames for the projectile to appear. This was recorded in 60 FPS, which means we had to wait more than 100 milliseconds. If we add input device latency, output device latency, and stuff like that on top of this, you can reach quite high values that are noticeable for the end user. But because of those distractions, it basically doesn't feel like it. Let's take a quick step back and let's take a look at our input latency chain once again. Let's think what this technique does to our input latency. It basically reduces this whole mess to something that resembles single-player experience. And the average perceived latency now is 131 milliseconds, which is pretty great value. It's pretty responsive gameplay. The next technique I'm going to show you today is client-side prediction. I really like this one. This is pretty neat. When we simulate local objects, we have inputs, and we typically run the same type of simulation on both ends, on the client side and on the server side. We can combine this powerful knowledge to predict what the server response will be, which means we can act on the user input without waiting for any network communication to happen. Its typical use case for this is player movement. Overwatch 2 as an example, and this was recorded in some additional software running in the background. You can see this box in the lower right corner of the screen. It displays my actual keystrokes. It displays what key I'm currently holding. Let's take a look frame by frame how responsive this is in real. This is before pressing any keys. And we know this because there is no box in lower right corner. It is being displayed only when I'm holding any key. And this is the first frame after the A key has been registered. In this game, A, of course, corresponds to moving to the left. Right now, let me switch between those two frames back and forth so we can see what really is going on. We can see that there is some small movement. It's not significant because there is some acceleration going on that we can observe when we progress further. But what is really important, it is immediate reaction without waiting for any network communication. And in top-down games, this distraction and this additional delay is all right, it's fine, you won't notice it. But again, you should know your game. In first-person games, this additional delay would render the game like annoying at best, unplayable probably, I mean. And that's why in those cases, we need to do better, and client-side prediction is one of the solutions we can use. Next use case for this technique might surprise you because I'm going to talk about projectiles once more. In Quake 3 Arena, gameplay experience is quite alright, but it turns out we can do better. And in modern games, we have more and more gameplay characters and weapons that shoot fast projectiles. And I mean, the projectiles themselves travel quite fast. And if projectiles, the faster the projectile, the longer the distance between the weapon and spawning position of the projectile. And of course, the longer the distance, the more obvious and noticeable for the end user it is. That's why in games like Overwatch 2, we can see quite clever use of client-side prediction, and it's basically used for projectiles. Farah from Overwatch 2, asterisk, not every weapon in Overwatch 2 is client-side predicted, only the ones that shoot fast projectiles. First frame before shooting rocket, the first frame of shooting sequence. We can see a lot of similarities between this and example from Quake 3 Arena. We can see those same distractions, the explosion, the weapon recoil animation, but can you see the difference? The difference is this shiny stone-like thingy in the front of the weapon. And this is actually our projectile. We can see it flies through the air, so this is definitely our projectile. And at this point, you might be wondering, okay, you mentioned that we can do as many things as we want on the client side, as long as we won't mess with the game state too much. Shooting rockets is pretty impactful, doesn't it? Well, it turns out we can split this into two stages. The first one is spawning the rocket and projectile movement. This on its own is not impactful at all. We can use client-side prediction for this without any issues. It's only for visual representation of the projectile. On the other hand, we have explosion and applying damage. This is pretty impactful for the game state. And this should happen exclusively on the server side. And that's what we can observe in Overwatch 2. Let's find our projectile. It's still in the air, so let's find frame when projectile hits the ground. It's around here. We can still see the trail because it doesn't disappear until the explosion happens, but the projectile is gone because it hit the ground already. Let's count frames. 1, 2, 3, 4, 5, 6, 7. We had to wait around 7 frames for the explosion to appear. This additional delay proves that there is no client-side prediction for the explosion itself. And of course, the explosion is in the middle of the screen, but what is more important is this white line in the lower section of the screen. It's the beginning of the animation after killing an enemy, which means this is the frame when the damage has been applied. Once again, let's take a step back and let's think what this technique, client-side prediction, does to our input latency chain. And you probably have guessed it by now, it does exactly the same thing as the distraction does. It reduces this whole mess to something that resembles single-player experience, single-player experience is probably the most responsive one that we can provide for the end user, at least input latency-wise. Client-side prediction is cool and all, but it comes with some caveats. Mainly, we can mispredict things. And when it happens, we end up with some kind of conflict that we need to resolve. The easiest solution we can apply is simple teleportation. We have mispredicted local object, we receive proper data from the server, and we apply this new state instantly, without thinking twice about this. It might seem like it would be really, really visible on the screen because the change in the game object state is quite abrupt. But in case of client-side prediction, it's not really that visible. It's because in 99% of cases, the client-side prediction is spot on. Conflict resolution is not required at all. And in vast majority in other cases, the distance to correct is so small it's not really noticeable. We're talking fraction of the pixel right now. Well, there are cases when this is visible, like really visible, but it's when network goes south. And truthfully, when network goes south, every technique you can imagine is visible, so I'm not sure if this matters at this point. Example from Diablo 3, and of course, this is when network goes south because it has to be visible to prove this. Let's focus on this main character in the middle of the screen. We can see client-side prediction allows for free movement in almost every direction, but the game server doesn't agree at all. The player gets teleported again and again and again to the beginning position. Of course, this is terrible user experience, but that's what happens when network goes south, and we have like all been there at some point in time. If you want to be more sophisticated, more fancy about conflict resolution, you can use interpolation. And I'm sure many of you are already familiar with the concept. Basically, instead of applying new state immediately, we provide smooth transition between our invalid state and the valid provided by the server over a short period of time. For client-side prediction conflict resolution, teleportation is probably more than enough. For remote objects, on the other hand, this is perfect use case for interpolation. Because for those objects, we do not have local inputs. We do not have local like client-side prediction at all. What we have is only snapshot-like data received from the server in semi-regular intervals. And the only way to provide smooth simulation for the end user is to use interpolation and interpolate between those known states of the object. It sounds far more complicated than it really is, so let's take a look at this schematic example. Let's say this is our enemy, and this is what we see on our screen. We receive data from the server, so we apply this to our local simulation. We calculate the trajectory, and we begin with the interpolation. In the meantime, we receive new updates from the server with updated position, so we take this into account and adjust our local simulation once again. And it happens over and over and over again. It's basically like we are chasing the latest known state, but never are really able to reach it. Like before, when everything goes according to the plan, it's not really visible. But when network goes south, well, this happens. Counter-Strike Go, let's take a look at this enemy in the middle of the screen. And we can see the enemy is being pulled towards the ladder in the matter of few frames. It definitely is visible that it shouldn't happen, but this smooth transition proves there is some interpolation going on under the hood. In some cases, we don't have, we managed to reach actually the end position, and we're still waiting for new data to appear. It just didn't come in time. Maybe we lost connection with the server for a second or two, or something like this. What can we do in those cases? We have two options, really. First one, don't do anything. Just wait for new data to come in, apply conflict resolution, and be happy about this. The second one is extrapolation. Extrapolation is basically playing a little bit of guessing game. We can assume the remote object is going to be doing whatever it has been doing for the last few frames. And frankly, guessing game is not the best algorithm for anything, but user experience is already affected. We didn't receive proper data on time. So guessing game might be your best bet in those cases. Hands down, worst case scenario for this technique are racing games, especially when we lose connection with enemy that is currently taking a turn. Of course, I have example. Forza Horizon 5. Let's take a look at this enemy, and this car ends out of the road, and then correction kicks in, and it's really visible when the correction kicks in. There is a lot of fun going on the screen, so let's take quickly this time, frame by frame, what is going on. This is the frame roughly when we lost connection with this car, so our game client assumes the car is going to be doing whatever it has been doing, which means driving in the same direction with the same speed, etc. Car ends up outside of the road, and then correction kicks in, and car ends up back on track over the course of few frames. What is worth to note here is that the extrapolation itself is not really visible. We keep providing smooth simulation for the end user, so it looks basically like our opponent went completely crazy and tries to hit the first tree he or she sees, but what is visible is the correction that happens afterwards. Next example from Fortnite. This enemy is barely visible, so really sorry for this. We can see the enemy is running towards the right side of the screen with like the same direction, constant speed, clear signs of extrapolation, and then the visible correction kicks in and the opponent ends up on top of the roof in the matter of few frames. This brings us to the last technique I'm going to tell you about today, lag compensation, and this one is quite tricky one. If distraction is like being street magician, this is more like being time traveler, which is a few levels harder to achieve if you ask me. This is probably must-have for every game, every first-person shooter game that uses recast-based weapons. It might be quite useful as well for games with melee weapons, like for Honor, for example, if you want to compensate for the latency when calculating the weapon collisions. As I mentioned, it's pretty complex, but let's start simple and build on top of this. Let's say this is our enemy, and he is running towards the right side of the screen, and this is what our server sees. This is point of view of our server. Let's add another level of complexity. Let's add our own point of view, what we see. I mentioned when I described the interpolation of remote objects that we are chasing the latest known state, but never are able to reach it, which means we are constantly behind the server just a little bit. The real fun begins though when we try to shoot this enemy. So let's freeze this animation in the middle, right here. Where do we aim? Of course we aim where we see the enemy, right? The problem is that's not where the server sees our enemy. And to complicate things even more, by the time the server receives data about us performing the shot, opponent is even farther away. Without this technique, without lag compensation, the things would just end up here. The server would do the comparison, would say, oh, you missed, no damage being applied, let's move on with the simulation. But of course we can fix this with lag compensation. Lag compensation happens on the server side exclusively, so let's forget about our local representation for the time being. And what server does, it goes back in time to see the world state the shooter saw exactly at the moment of performing the shot. It sounds complicated, it's not really that complicated, so let me say this again. Server goes back in time to see the world state the shooter saw exactly at the moment of performing the shot. And that, of course, it's pretty fast, it happens almost instantly. Server goes back in time, does the comparison, goes back to the current state, and moves on with the simulation. It's far easier to do this in PowerPoint than in real game, by the way. That's not even the craziest part, because those two representations of our object, like our point of view and server point of view, are not the only ones that are in play, because there is also our enemy and his or she's point of view, or her point of view. Basically our enemy probably uses client-side prediction, which means our opponent is even ahead of the server. And the key point to note here is that the distance between what our opponent sees and what we see can be quite large, and this has serious consequences in games. Example from Battlefield 1. We can see our enemy rushing forward to reach this small room. And of course we aim, we pull the trigger, we aimed perfectly fine, so the damage is being applied few frames later, right now. From the point of view of the shooter, everything looks perfectly fine. We aimed at the enemy, directly at the enemy, pulled the trigger, and the damage has been applied. But from the point of view of the player that received the damage, it's pretty unfair, isn't it? He thinks he's perfectly safe. He reached the small room with no enemies inside, perfectly covered from all sides, and still managed to receive damage from the enemy. That's why I call this technique necessary evil, because on one hand it can provide controversial situations as best, but on the other hand it provides us great shooting experience in first-person shooting games. I cannot imagine a world without this technique, because without this, we would need to aim in front of the enemy every single time, and we would need to adjust the aiming distance based on the network latency, which is plain madness if you ask me. As game developers, we definitely need to be aware of consequences of using techniques such like this, especially when we work on esports games, because we need to make sure impact of such techniques are minimized, especially during live major important events, to avoid controversy, of course. Great news, you survived the presentation. I survived the presentation, so congrats for you, congrats for me. And the techniques that I showed you, those are the tip of the iceberg, really. I selected those specifically because in my humble opinion, those are the most important ones, and those are the most common ones. I mean, we can see them in almost every online game out there, maybe except lag compensation. This is more use case specific, but it's still pretty common. If I were to choose one thing that is most important to remember after this talk, it would be probably that what matters in the end of the day is end-user experience and what user feels when playing the game. Those techniques can improve this feeling of the gameplay, and that's why it's worth using them in your games. If you're still starving for more, here are some cool sources that you can use to broaden your knowledge. And if you have any questions and for any reason don't manage to ask me today, feel free to use this email. I'll show the QR code in a second if you prefer to scan it instead. And yeah, I hope you find this useful, and I hope you can use this knowledge as a foundation for building your own expertise. Thank you very much. Jeez, I was rushing, so we have time for questions. Any questions? None. Okay. Okay. A microphone.
Hey, thanks for the great talk. So in the lag compensation technique, you mentioned that the server goes back in time to check if we manage to hit a target or not. How do you know how much in the past you should go? Because the latency is variant probably from frame to frame. So how do you know exactly how much back in time you need to rewind? Are like the frames counted and you know exactly to which frame you need to go back?
It depends on the game. I mean, I saw a few implementations. One of them was sending basically exact timestamp. I'm not sure if this is the best idea because it's quite easy to abuse this. Like you can alter the client and send other data, maybe not aimbot, not aim cheat, but it can still abuse the consequences of performing the shot. The other one is basically you are right that it might be different between frames, but generally using some heuristic on the server side and measuring latency between the client and the server is just enough to do the job. So basically, yeah, we have this data about the latency on the server side, and we can use this. And we typically do not react for some, big changes over a short time. We use value that we calculated over longer period of time.
Thanks. So if no one other have, I have one more question.
Okay.
Yeah. So what are the typical techniques to store this game state from the past? Because apparently you need to store multiple frames, multiple snapshots of the unit positions. So I don't suppose you implement with the databases. You probably keep a simple buffer to only keep the recent 60 frames or something like that. That's exactly what happens, and of course once again it depends on the game because I saw different implementations. I saw games that had game state in continuous memory, and the games were able to dump this whole memory section into the buffer, and basically restoring the position was quite fast, and it was simple to manage those states. But there is Unreal Engine movement component that has, but it uses client-side prediction, not lag compensation. Sorry, that's true. But it counts some positions as well for adjusting the position and providing smooth simulation for buffering purposes. I didn't have time to talk about those really. And in those cases, the object itself records some positions, some states. It holds it in some kind of a vector, and then of course with timestamps to know what time it corresponds to, and it can use this to provide the simulation. I hope this answers your questions.
Perfect, thanks.
Hey, thank you for the great presentation. In order to do client-side prediction, you have to duplicate the code that you have on the server side. How do you deal with the logic maybe becoming misaligned over time, if that happens?
Okay, I would say that in games I worked on, it didn't really happen because we used Unreal Engine, which have fairly the same logic on both ends. But from other games and my experience, I would say the best way would to have some kind of automated testing that makes sure the logic on both ends is exactly the same. Basically, you provide input for the simulation you run on the client side, and you provide the same input for the simulation on the other end, and compare the results. And if you do this after each submit, you know when something is fucked up and you need to fix it, basically.
Okay,
thank you. Do you think 60 or more tick servers are like a good way to resolve these lags, or it's just a money burner?
I think it's a pretty good way. It can reduce the lag quite significantly. Especially in those cases like lag compensation, it can minimize impact of this technique big time. But of course, not every user is able to maintain those high network frames. That's why we tend to see those higher network ticks in live events. And in some games, we have logic that manages this dynamically. If all players have great connection, the server brings up the network tick, and it minimizes the latency. And when something goes wrong, it lowers it, and it manages this way. So I would say yes, this is perfect way to do this. But if you want to provide great experience for everyone, we probably should like at least test this, right? It depends, yeah. Thanks.
Okay, any more questions? So, thank you so much once again.
Thank you very much once again for being with me here.